So today's video is part 2 of pH calculations and the third video in our series of acids and bases. So now we're going to be looking at how we calculate pH of water. So water does ionize slightly, setting up an equilibrium. And so by ionizing, we mean that water sometimes some of the molecules will release H plus and OH minus ions. However, as we say, this is an equilibrium because only some of the water molecules will actually ionize into these products. And because water is releasing H plus ions, it can act as a weak acid, and this is because it is only partially dissociating. So it can act as a weak acid. And weak acids, as we saw in the previous video, can use Ka as the equilibrium constant. And so we can say that Ka is H plus times A minus, which is our OH minus ions in this case, over our Ha, our weak acid, which in this case is water. So we can say this. However, because water is present in excess, because it is the solution, the concentration of water can be left out of the equation. And so we get this. Kw is our concentration of H plus times our concentration of OH minus. And this Kw is called the ionic product of water. And this is a new equilibrium constant. And this is what we use for water. So because water ionizes partially into H plus and OH minus, it can be seen as a weak acid, allowing us to set up its Ka equation using the generic Ka equation. But because water is present in excess, we can leave the concentration of water out, leaving us with our new equilibrium constant, Kw. So we now have our Kw equilibrium constant equation. And at 298 Kelvin, Kw has a constant value of 1 times 10 to the minus 14. And Kw, as any equilibrium constant, is temperature dependent, because at different temperatures, water will release more or less hydrogen ions. So at 298 Kelvin, so at standard temperature, it has a constant value of 1 times 10 to the minus 14. But what does this mean? So this means if we plug our Kw into our equation up here, we have this equation, and because our OH minus and H plus are equal using our Ka assumptions, because these also apply here, because for every water molecule we release a H plus and a corresponding OH minus. So our concentration of H plus and concentration of OH minus are the same. So we can say that this is equal to H plus squared. And then we can then square root both sides to find our H plus, which is 1 times 10 to the minus 7. And then putting this into our equation, minus log of the H plus concentration, which we found to be 1 times 10 to the minus 7, gives us a pH of 7. And so water is neutral at 298 Kelvin. And then as we said before, because Kw changes with temperature, this is the reason why water is not always of pH 7, why water is not always neutral. Because as temperature changes, this Kw changes, meaning our H plus concentration will change, changing our pH. So now moving on to strong bases and calculating their pH. So strong bases fully ionize in water. So a strong base is sodium hydroxide, for example, and this reaction will go to completion and all of the strong base molecules will form Na plus and OH minus. So fully ionizing means that all of the basic molecules will form its ionized products in water. And because this reaction goes to completion, the concentration of our strong base, so in this case our sodium hydroxide, is equal to the concentration of OH minus ions it releases. Because as the reaction goes to completion, we don't need an equilibrium constant to tell us how much of our ionized product we have formed. And so, however, strong bases, as we see in this equation up here, do not donate H plus ions. And so we cannot use a Ka equation like we did with water. And this is because our strong bases cannot act as weak acids alone. So we cannot use a Ka. However, our strong bases do release OH minus ions, as seen in this equation. And we have seen a equilibrium constant, including OH minus ions. We've seen Kw as we have introduced in this video. And this allows us to be able to find the H plus concentration in our solution, because even though our strong base is not directly releasing or uptaking H plus ions, it is the H plus ion concentration in our solution which is going to help us to calculate the pH. So we still need to calculate the H plus concentration even though we're dealing with a strong base. And because it is a strong base in water, we are able to use the equilibrium constant Kw because the water is at an equilibrium with the water ionizing. And so even though our NaOH isn't in equilibrium, the water is, so we're able to use this constant here to rearrange to find our H plus. So we can now sub in our new concentration of OH minus ions, because this equation here is of our water, so our H plus and OH minus of a pure water solution will be equal. However, we have introduced a strong base, and this is fully ionized to increase the OH minus concentration drastically. So we can sub this new concentration of OH minus ions into our equation, and then we can rearrange to find our H plus concentration. And we can discount the OH minus concentration from our water, and this is because it will be so tiny in comparison to our strong base, it won't make a difference, and this is because water only very partially ionizes. So if we look at an example, we want to find the pH of a 0.1 mole per decimeter cubed solution of sodium hydroxide at 298 Kelvin. So first we recognize that this is a strong base, realizing we need to use our Kw equation. So at 298 Kelvin, as given in the question, we know that Kw has a constant value of 1 times 10 to the minus 14. So we can sub this value into our equation, so Kw is 1 times 10 to the minus 14, times our H plus concentration, which we want to find, multiplied by our new OH minus concentration, which in the question has been given as 0.1, as this is equal to our OH minus concentration because our sodium hydroxide fully ionizes. And so we then rearrange to find our H plus concentration by dividing both sides by 0.1 to give us this value here. And then now we have our H plus concentration of our solution, we can sub it into our pH equation to get the pH as 13.